Okay, this is our first lecture of quantum mechanics in which we have to deal with postulates. So there is first postulate in which there is some observable quantities. Okay, like you have energy, linear momentum, angular momentum, or number of particles on. Okay, so for this you have to select the eigenvalue equation in which there is some operator you have to operate on it. Okay, and which generates the eigenvalue with eigenfunction. So let's go to the derivation. You can understand very well after that. Okay, so there is a operator you can see in which we apply some operator on momentum. Okay, this is the linear momentum. In quantum mechanics already we have some values operators on some observable quantities that we have to be remembered. Okay, so here first we have to find the there is a condition that we have to find the eigenfunction and eigenvalue of momentum operator. So for this is the eigenvalue equation. You can see there this is the operator on momentum with eigenfunction, and after applying this operator on eigenfunction you will uh, give what some eigenvalue which shows with this simple p which shows momentum. Okay, and with eigenfunction. So we have to substitute p value. This is the p operator value. You have to substitute in this above eigenvalue equation. So after substituting, these they'll change into the first order derivative. You have to select the axis in which direction you have to find your particle. So here when you want to be find the particle position, you have to check the probability. You have to calculate the averages of particle. So these mode square of eigenfunction with some x's is the probability of finding particle in some momentum space. So you have some interval like for x to x plus dx. So there is a probability of particles to be present. So for free particle you have these eigenfunction. Okay, so what is a? A is the amplitude of the particle. Okay, and these shows the obvious exponential notation where I is the imaginary number and k is the wave number. Okay, and x is, you can say, this is the position. So in quantum mechanics, wave number is related to momentum. Okay, and these h cut, these shows the reduced in Planck's constant. You make sure this is the reduction in Planck's constant. This is not only the Planck's constant. Further, the eigenfunction is the periodic function. These means that wave function repeat itself at regular interval of these lambda shows. Okay, so when you have different numbers, different intervals, so now you can see this is the periodic function, so there is some addition in the position. So you can see this is lambda shows there is increase in position. So further you can see, and after dividing these term again with both sides you will get, okay, okay, after dividing these terms, okay, on both sides you will get 1. You can see there, and these terms will be cancelled to each other. Okay, and you will get 1, and you have to applying this summation individually on both exponential notations. Okay, with cancelling these terms, and you will get simple the lambda value. Okay, so here you have to find that the value of this 1. Okay, okay, for this, these by Euler formula. Okay, by Euler notation. Okay, these values exactly equals to cos and where in the power some constant k lambda plus iota sine k lambda. Okay, so you have to select the values in order to get 1. Okay, so you know that k lambda should be equals to 2 pi. This is the rotation of 360 degree. Okay, so after completing one phase you will get cos k lambda equals to 1. Okay, k lambda, when you put 2 pi instead of k lambda and taking cos what 360 you will get 1, and sine 360 you will get 0. Okay, further now we can see. Okay, by de Broglie relation. Okay, now you can see by de Broglie relation, you know the momentum is equals to some inverse of wavelength, and this is the de Broglie relation. And when we talk about in quantum mechanics, so the wave number is related to momentum, and this is the wavelength which is inversely proportional to the momentum. So eigenfunction of momentum corresponding to the eigenvalue has a wavelength, that is de Broglie wavelength. So when we talk about the eigenvalue equation, so there is some eigenfunction, okay, and there is eigenvalue. So these should be considered as a de Broglie wavelength. Okay, uh, further, so the eigenfunction and the eigenvalue, here is it. Okay, momentum in quantum mechanics is related to wave number. Thank you. This is all about from my side.